Okay, class. Here is the second part of the TNOTES for the simple harmonic motion, and that is section 9.1 for the HL. In motion with a pendulum, the gravity produces the restoring force. Look at the diagram below. The bob, which is right over here, it's hanging from the ceiling, is in equilibrium across the radius, which is right here, when the tension equals the weight component, the mg cosine theta, the y component. The x component, which is parallel to the weight, which is right here, is not in equilibrium, and it provides the restoring force as the object swings back and forth. We begin with F equals ma, which is true for all objects. We also know that acceleration for simple harmonic motion is a equaling negative omega squared x, which gives us F equals m omega squared x, and that is negative. And that is just from supplementing, and that is just from substituting acceleration into the F equals ma equation. This F is the restoring force, and looking at the diagram below, we know that the x component is the mg sine theta. So restoring force is the mg sine theta. Now we have mg, or negative mg sine theta, equaling ma. And that is just because we just took this mg sine theta and we plugged it in for the force. And now we have this. When we substitute this into our equation, we get mg times x divided by L equals ma. We cancel out the m's, and we have a equals negative g times x divided by L. Okay, so here we have the same equation, the a equals negative g times x divided by L. We also know that acceleration equals negative omega squared x. When we plug that in for acceleration, we get this, which is omega squared equaling g divided by L. We know that angular frequency is distance divided by time, shown by the equation here. And that is angular frequency equaling 2 pi divided by the period. We plug that in for omega, which is here, and now we have 2 pi divided by t squared equaling g divided by L. When we solve for t, we get this answer here. And we have t equaling the period, and we have L being the length of the pendulum, and g for gravity. Let's get the equation for a period of a mass spring. What we know from already studying springs is that the force equals a k constant times x. And remember, this is the spring constant. And we also know that F equals ma. When we set these equal to each other, then we get negative kx equaling mass times acceleration. To incorporate the elements of simple harmonic motion, we need to substitute something. So we know that we can substitute for acceleration because we have the acceleration for simple harmonic motion, which is omega squared x. When we plug that in, we get k equaling mass times omega squared. We also know that omega equals 2 pi divided by t. Plug that into omega, and we get k equals m times 2 pi divided by t squared. This gives us our new equation, which is t equals 2 pi times the square root of m divided by k. Here is an example for a mass spring. It is known that a load with a mass of 200 grams will stretch a spring 10 centimeters. The spring is then stretched an additional 5 centimeters and released. Find the spring constant and the period of vibration. Go ahead and solve this and then restart the video. Using the equation for springs, we have F equals Kx. We solve for K to find the K constant, the spring constant. We have force equaling mass times acceleration, so we have the force as being the mass, which is 0.2 kilograms times 9.8 meters per second squared, and divided by the length, which is 0.1 meters. Your answer for your spring constant is 19.6 Newton meters. To find the period of vibration, we are using this equation here, which is T equaling 2 pi times the square root of mass divided by your spring constant. Here we have our mass, which is 0.2 kilograms, and 19.6 Newton meters. And when we solve for that, everything crosses out, and gets a little hairy in there with some of the units of measurement, but everything comes out to be seconds since it is the period. And we get a total of 0.635 seconds. When determining energy in simple harmonic motion, we need to derive an equation that will incorporate both energy and simple harmonic motion. So we are going to use the energy equation here, which is the kinetic energy equaling 1/2 mv squared. And we use this equation here because they share the same variable velocity. Subbing the velocity into the energy equation, we get the following equation. And this is, of course, after you simplify. To find the maximum kinetic energy, you need to set x to 0, and then you are left with this equation here. To find the potential energy, you just need to take the total energy and subtract the kinetic energy from it. When you do that, you get this equation, which is also located in your data booklet. And that is 1/2 mass times omega squared x squared. Here's an example for you to try. A mass spring system oscillates with an amplitude of 3.5 centimeters. If the frequency is 3.56 hertz and the mass is 0.50 kilograms, determine the total energy of the system, the maximum speed of the mass, and the maximum acceleration. Go ahead and start this video back up when you're finished. Let's go ahead and find the total energy of the system. We have the mass, which is 0.5 kilograms. We have x sub 0, which is the amplitude at being 0.035 meters, and we have the frequency of 3.56 hertz. To find the energy of the system, first we need to locate what is the angular frequency. We find that by using this equation 2 pi f, and we know that the frequency is 3.56 hertz, which gives us a total of 22.36 radians per second. We plug that into our equation for the total energy, and the total energy is going to be 1/2 m omega squared x sub 0 squared. When we plug all of our information in, we get a total of 0.15 joules after you take into account significant figures. The maximum speed of the mass when x is 0, so this is when kinetic energy is at its max. So at this point, the total energy is all kinetic. Here we have E sub k, so kinetic energy equaling 0.153 joules equals 1/2 mv squared. Solving for v gives us an answer of 0.78 meters per second. The maximum acceleration when x equals the amplitude, here we have the acceleration equaling omega squared x, and the max is going to be omega squared x sub 0 because you're going to be going your fastest, or your acceleration will be at its highest when you are at your furthest from the equilibrium point. So you have 22.35 squared times 0.035 equals 8.7 meters per second. All right, so we have completed our HL TNOTES. Be ready to use this information in class next. Have a great day.